Great. So welcome everybody once again. I'm Paweł Tomasik and I work for Motorola Solutions, as was mentioned during small talk. And today I'm going to talk about asynchronous HTTP client, its anatomy and traps. You may wonder why there is yet another talk about asynchronous programming in C#. There were hundreds or maybe even thousands of them already. However, as you join that talk, you probably expect to hear something non-obvious, and I will try not to disappoint you. In the meantime, feel free to raise your question in the chat. At the end, there will be short Q&A sessions, so maybe I will try to answer them. To be honest, I'm going to reach the topic of HTTP client in the second part of the presentation. Right now, I'm going to start with basics. However, I'm not going to talk about how to use async awaits in the code because it's something that you probably do every day. Instead, I will focus on how this stuff is actually handled by C# compiler and .NET environment. Not because this knowledge is absolutely required to write good asynchronous code. Actually, there is a group of people which personally I belong to that simply likes to know how the tools that they are using every day works under the hood. So let's start with the short demonstration. The tool I'm going to use to investigate the internals of async awaits is a sharplab.io. It's a free online tool that, among others, allows to compile and decompile C# code. What you can see here on the left side panel is just our input code, while on the right side panel, there is a code which is a product of compilation and decompilation in our input. So for the Hello World application, both sides look more or less the same, apart from a couple of assembly annotations added on the right side panel. Let's see what's going to happen if I change the signature of the main method and we'll make it an async one. So what we can see immediately is the amount of the code here is increased significantly. Before we proceed, I will add at least one await statement to have, let's say, first class asynchronous method. So I will add task delay. Okay. And if we scroll down right now, we can realize that there are actually no more async awaits there. Our method is somewhere in the bottom, and it is stripped of async keyword from the signature. And moreover, it actually does not contain our original logic. So nothing about hello world or this delay. So where it has gone? Actually, our logic was moved somewhere to the top, to the object, which is declared here. It was auto-generated object created by the compiler, which is actually a state machine object. It implements this async state machine interface. And somewhere in the middle of that object, there is a method called moveNext, and somewhere inside that method, there is our logic. I would like to spend a few more minutes on that conversion. I mean, what the job that compiler does from our original method. However, this code, this auto-generated code, is a little bit difficult to read, so I prepared a simplified version within the slides. The only conclusion from that demonstration I would like to highlight is, first of all, that async await keywords are just compiler features, and they are transparent actually to the environment. So we have this code with 100% parity on the left and right side panel, but the right side one does not contain those keywords. And the second thing is that this async method was actually converted by the compiler to two artifacts. So to the method itself at the bottom, and to this state machine object. How they look in more details, so I'll just try to show that in the presentation. So let's go back there. And to analyze that, we'll just take simple async method as an example that at the beginning invokes some synchronous operations. Later on, it awaits some task. It proceeds with other portion of synchronous operation, one more await statement, and finally, the last segment of synchronous code. And as we have seen on the example, this kind of method would be converted by the compiler to two artifacts, to the method itself and to the state machine object that is implementing async state machine interface. So let's take a look what we have in that method, first of all. The first thing we can find in that method is the creation of the new instance of that state machine object. So the one that was generated. Later on, the builder class is created. This is auxiliary class that is able to wrap the state machine and eventually is also able to return the valid instance of the task object at the end. We will see that in a moment. Next step is the setting the initial state. By convention, it is -1. And we are starting our machine and returning that task instance that was provided by that builder. However, the core of this asynchronous logic, of course, resides in that state machine object. So let's zoom in and see what we have inside. Inside that state machine object, there's, of course, the internal field that represents the state. And it has this move next method, which is actually defined by this async state machine interface. And inside that move next method, there's a switch case statement over actual logic of our method. So here, actually, this code that we written is somehow converted inside that switch case statement. How? So let's zoom in again. How this switch case statement looks like. In initial state, I mean this -1, we are executing simply the first block of synchronous operations. Actually, it's every line up till the first await that is located in our async function. Later on, the state is incremented to 0. And now the core element here is the callback registration phase. This await statement is somehow translated to the callback registration. I mean, the state machine registers its move next method, so its main method, as a callback to be executed by task 1 while it is completed, and returns. So actually, instructions up to this line are the ones that are executed immediately when we are invoking every async method, because the first invocation of this move next method goes together with starting the machine. So when we are invoking async method, we are executing all instructions up to this line and returning after callback got registered. And the async flow resumes when the callback is triggered. So the move next method is executed again. And as the state was set to 0, we are moving to the next block, which contains the second portion of synchronous operations. So everything that is below await statement till the next await statement. We are setting state to 1. Again, we are registering callback with the same move next method against task 2 and returns. And in the final state, in that case, we have a similar sequence, but there is no more need of registering callback, as that's a final state. So that's more or less how this conversion looks like. So what happens when we are writing async method? We know that the compiler will generate those artifacts, which looks like that. So right now, we can move to the pretty fundamental question for all this idea. Who is responsible for resuming async flow? I mean, who actually calls that move next method when it is necessary? What actually happens when we are awaiting async methods? But wait a moment, I've said awaiting async methods. Is it something that we are really doing? I don't want to be picky about wording, but just want to be 100% sure that we are on the same page as for terminology before we proceed. The first thing I wanted to clarify is that we are actually not awaiting methods, but objects. I mean, this kind of expression is about awaiting a return value of doAsync work method, not the method itself, which can be easily explained if we split the invocation of method and await statement. And the second thing is that the async keyword is something that tells the compiler that it needs to convert the method into the non-async method and the state machine. And it has nothing to do with the way how the method is called. I mean, in this particular example, the possible implementation of the async work method might look like this. So it may be an async function, but it also might be regular non-async method that returns task instance explicitly. So if we were to fix the header of that slide, we should rather say that's all about awaiting objects within async methods. By the way, if we take a closer look at this example on the bottom, one thing I want to highlight is that when the method is async, we are not actually returning explicitly the return value that matches the signature. So there's no return statement there. We are not returning that task. So that responsibility got delegated to this auto-generated code, as we see. Of course, if we have non-async method that returns task, we need to return it explicitly. And that's actually the reason why only few return types are allowed as a return types for async methods. I mean, those are types for which compiler knows how to generate those state machines. And it's not those types that are not the only ones which could be awaited, because here the set of requirements is a different one. So what they are, how to create, for example, custom awaitable that will look like that and will not use any built-in awaitables available in task package. So something that will be created like new my awaitable, and that will return some value of type T once awaited. What kind of requirements needs to be satisfied? The intuition says that probably my awaitable class needs to implement some interface. However, for some reasons, I would say pretty good ones, there is no such interface. Instead, there is a duck typing convention used there. I mean, compiler directly explicitly checks if this class contains getAwaiter method that returns a myAwaiter object. I mean, the return type of that is a valid awaiter. And what does it mean? I mean, valid awaiter. So here is additional set of requirements. The class to be called awaiter needs to first of all implement iNotify completion interface, which defines a single method, uncompleted one. However, in addition to that, there are two more methods that needs to be present in the awaiter, which are not member of any formal interface. This is getResult and is completed. And here also this duck typing convention is used. So compiler directly checks if those methods exist or not. What those methods actually do? The first one is a setter. It is a setter that can be used by the caller to register the callback. So by calling that method, the caller can say that I want this method to be invoked while you produce your value. The second method, getResult, is supposed to return the value in a blocking way. It means that if value is not yet available, it shall block the caller's thread until the value is produced and then return. And the last item here is completed property, which simply allows to check if the value is produced or not. By the way, if we see how these requirements look like, we can realize that they are actually provides a guarantee that for every awaitable, not only for tasks, but for every awaitable, you can call getAwaiter.getResult to achieve to return the value in a blocking way. And those methods are not member of any formal interfaces. It's only duck typing convention that is checked by compiler. As we know what kind of methods are available for awaitables and awaiters, we can try to figure out how they are used. I mean, how this generated code, the state machine, actually uses that method. What happens when our code hits await statement? The first thing the state machine does is calling isCompleted property to check if value is already available or not. And if not, which is default case, it uses this onCompleted method to register the callback, register its moveNext method as a callback. So that's the step we've seen in one of the previous slides, this pink one, when the state machine registers the callback, the move next method as a callback for a task. It happens exactly here. And that's actually the answer for the question we stated, who is responsible for resuming async flow? So the answer is that it is the awaiter. No, it's the entity that is supposed to call that callback when necessary. And once it happened, the next thing the state machine does as a way of handling that callback, it calls getResult method to receive value and returns. There is also a shorter path available here. Of course, it may happen that isCompleted returns true immediately. And in such a case, we are skipping that callback registration phase and returning completely synchronously immediately to the return statement. You may wonder how it is possible that getResult method, which is by definition blocking, and the usage of that is the well-known anti-pattern of asynchronous programming, is executed by this auto-generated code inside regular async flow. So the reason for that is that there is an implicit assumption about getResult method that needs to be satisfied by any awaiter, that getResult method returns immediately in those two cases. I mean, if isCompleted return true at the very beginning on or after the callback got triggered. Actually, there are more such kind of implicit assumptions that that state machine code leverages from. And those are reasons why implementing custom awaiters, it's not something really recommended. However, for the sake of science, we'll try to do it and to verify if that flow is actually what is executed by the generated code under the hood. So I invite you to the next demonstration. So within that code, I'll try to implement this myAwaitable class within that sample. So when trying to create a myAwaitable instance that is supposed to return some string, DAG string, after some delay. And that's supposed to be printed out to the console within that line. Right now, compiler complains about the fact that I'm trying to await a non-awaitable object. So let's see what is missing. Probably some of those requirements that we just discussed are not yet met. So let's see how this myAwaitable class looks like. It already contains that getAwaiter method, which returns awaiter, which is declared as an internal field and instantiated inside the constructor. Both parameters are passed to the awaiter, as actually the core logic is usually inside the awaiter. So this class looks okay, nothing more to be added, and that was the only requirement. However, this myAwaiter class is not yet completed. It misses something. So let's see how it looks like. MyAwaiter class already implements iNotifyCompletion interface, which defines onCompleted method. As you may remember, onCompleted method was supposed to be a setter that allows to register a callback. What we are doing here is just copying the reference that is passed here to some internal field for the future usage. And additionally, while logging the fact that callback got registered using some auxiliary method I added here, that in addition to printing out actual string, it attaches also the thread ID. What is missing here are those two methods which are not member of an iNotifyCompletion interface. So I mean that getResult and isCompleted. Before I add it, I need to declare internal field that will be used to store our value. And if I have that, I can add getResult method. That will simply return that value. And I will add also that isCompleted property. Which can be implemented as an auto property. That will simply check if the value is null or not. The only thing that remains is to create a way that will produce that value after some amount of time. So as the purpose of that exercise is not to use any built-in task method to see how this kind of elementary awaiter can look like, I will use the most primitive way that anybody can think about it. So I will create a new thread here that will sleep for a moment. I mean this delay time, and after that time it will copy that value and start that. So that's all. If we scroll up right now, we can see that there are no more complaints. So we can try to run that code. So let's see what's going to happen. As we can see, the code got started, and we can see this registering callback line. So it means that our state machine somehow internally verified is completed property to see that the value is not yet available because it was set to nulls. And because of that, it called this onCompleted method, which we can see that it was logged, registering callback. However, at this point, our code stacked. The obvious reason for that is that we did not invoke that callback. So let's terminate that and fix the problem. The callback is supposed to be called when the value is produced, so the good place for that is somewhere there. So I will just add explicit invocation of that callback here. Additionally, I will add some more logging before callback and after callback to see how the logic looks like. And if I run that again, we can see that we did not stack this time. Application got started in some thread 1, callback got registered, and our result was printed out. So this line, I mean, got executed. The surprising thing at first glance might be that while actually our last line of our main method is not the last line that is printed out to the console. Actually, we just verified in that way that this callback that got registered and invoked here was nothing more than move next method of the state machine that was created from our main method. And that state machine inside the move next method in the last invocation shall contain the last piece of synchronous code. I mean, everything that is below the last await statement, which is the last line. So this line was actually packed as a callback that was registered and invoked. And this is why we have before callback, our last line, and after callback printed out here. We can also verify this shorter path, I mean, the one where the value is available from the very beginning. So I mean, instead of that stuff, I will just provide that assignment immediately and see how the code is going to behave right now. So in this case, we have only start and result statements. So this whole callback registration phase was skipped. And both those lines were executed in the main application thread. And the previous example was seen that that this last line was executed in the different thread. Actually, that was the one that was started explicitly. Within that demo, I've shown how to create a custom awaitable that satisfies compiler requirements. However, actually, I did not create an asynchronous code. Of course, the main thread of application was not explicitly blocked by the await statement. However, I created another thread and put sleep inside. So the conclusion of that is that async awaits are not actually providing the asynchrony to the code out of the box. I would even risk the statement that they are not providing asynchrony at all. Actually, here we are assuming that this asynchrony is provided in some other way. What async awaits actually provides is that they are really convenient tool, really useful one for combining and managing asynchronous APIs. And this combining word is a keyword here. Without async awaits, creating a complex application that leverages from, let's say, classic callback-based asynchronous API quickly leads to creation of callback hell, which is pretty well-known effect for everybody that has experience, for example, with some early versions of Node.js. However, the core of, let's say, asynchrony, I mean non-blocking threads, is something which is delegated to the awaiters implementation, at least in case of C# and .NET. And this awaiter responsibility to invoke the callback when it is necessary, ideally without blocking any thread. And how it happens? No, actually, the answer is no, it depends. It depends on the particular implementation. So in real-world applications, when you are using elementary asynchronous APIs like task delays, like semaphore slims, or asynchronous I/O operations, we are leveraging from that smart implementations provided together with .NET library that is able to do it in some way. And today I'm going to focus on this last group, I mean I/O operations, taking on as an example HTTP client to see what kind of smart logic is used there to achieve this asynchrony effect, I mean effect of non-blocking a thread. Let's go back to the presentation and start with the beginning. What happens when our application code tries to execute an HTTP request against some host using .NET API? First thing it is reached here is an entity called HTTP connection pool manager. You may wonder what the HTTP connection actually is, while this protocol is by definition stateless. Of course, the protocol is stateless, but under the hood it uses a transport layer like TCP, which obviously contains the concept of connection, and establishing such connections, especially when it comes to SSL handshake, is by no means easy, I mean trivial nor fast. So that's a really good reason why the environment caches those connections in the pool. Actually creates a pool for every endpoint that our application talks to. So the pool manager picks the right instance of the pool that is associated with the host. And inside that pool, we have one or more transport layer connections. Some of them might be already busy by handling some other requests. So it picks the first idle one and takes an attempt of executing HTTP request using regular low-level TCP socket. And in most simple scenario, it boils down to executing first send async method to send the request, and later on to invoke receive async method to get the data back. Both of this method, the socket API are async ones. So callback-based API is provided by the socket itself. So let's zoom in what we have inside the socket. Important note about this slide and the next one actually is that it became an operating system specific. And I picked the Unix subsystem as an example. So what we will see here is specific for this operating system. We have our send and receive async methods there, and both of them have similar signatures. I mean, they are taking a buffer and a callback, among others, of course, as arguments. The obvious difference is that in the case of send method, the buffer is supposed to be filled by the caller, while for receive method, the buffer is filled by the socket. And in both cases, the callback is the reference to the function that is supposed to be triggered by the socket when it's done with its operation. Those methods are handled by entities called send and receive queue, respectively. And those entities, to execute their operations, are using heart of the socket, which in case of Unix system is a file descriptor. It can be also called socket handle or socket descriptor. Anyway, it's a low-level system API that could be used by the application layer to execute I/O operations. And this API exposed by operating system also comes with two flavors there. I mean, blocking and non-blocking one. However, in non-blocking mode, there is still no concept of callbacks. So what happens when we are calling receive methods in a non-blocking mode to get, for example, 10 kilobytes of data from our descriptor? So actually the method tries to do as much as it can without blocking the caller's thread. So if, for example, there is only 5 kilobytes available in an input buffer, it will return 5 kilobytes and return immediately. So of course, it might happen that this operation is not executed entirely. This is why those entities are called queues, because they simply queue the operation if they are not able to execute them immediately. So the question arises, okay, who is going to trigger those queues to ask them to take the next attempt to access the descriptor? The downstream API here is a handle events method, which is exposed by a sub-entity called poll event handler, which is responsible for dispatching those events to the send or receive queue. However, it does not do it directly. Instead, it uses a thread pool to dispatch those events. Why it is that? Why it's not just simple routing? So the answer for that is that together with every operation in those queue, we have that callback reference, which is supposed to be executed while the operation is done. And as we have seen in the previous slides, within this async generator, I mean this state machine generator, those callbacks will be probably our move next methods that contains most of our application code. So in that way, our application code is actually executed by this thread pool. Thanks to that, we have this appropriate delegation of responsibility. So our code is executed by a thread pool, not by someone who calls handle events method. And on the other hand, the handle events method got guarantee that it would be really lightweight. And this is really important. Why? Let's see the next slide, which will try to answer who actually calls that handle events method. And that responsibility is delegated to the entity, which in case of Unix systems is called socket async context loop. It is a thread that executes a blocking system call using poll method. Poll is a system level method that allows to register for set of file descriptor, so multiple file descriptors, which in this case are actually socket descriptors, and ask the operating system to be awakened when at least one of them got available for read or write, depending on what was requested. So when this method returns, we actually get the list of activated descriptors, socket descriptors, and we know which socket instance to ping. So that's actually what happens here. We are picking the right instance of the socket because we know that the descriptor inside that socket got something for us or got available for writing. So we are able to ping the right one. And thanks to the fact that handle events is supposed to be really lightweight, single instance of the socket async context loop is able to handle multiple socket connections. In Windows, there is not such entity like socket async context loop. Instead, there is a concept of I/O completion pods. The implementation is a little bit different there. However, the core idea remains the same. I mean, the idea where single thread is able to handle multiple socket connections. To be precise, in both cases, I mean Unix and Windows, there might be multiple instances of those engines. I mean these loops or I/O completion pod threads. However, their number is not related to the number of open socket connections. It's strictly a function of number of processors available to the .NET environment. So what we are leveraging here is that we are using that smart multiplexing logic, which is the next keyword I would like to highlight, to reduce number of threads that are involved in blocking system calls to handle I/O operations. But this number relies only on the number of processors available. And moreover, those threads are hidden deep inside the environment. Thanks to that, the API exposed to the end user is really convenient. First of all, it is the callback based, and later on, the Async API is built on the top of that. So it's not actually about non-blocking threads, it's about blocking fewer threads. And that's more or less all I wanted to say about socket anatomy. At the beginning, I mentioned that there will be some section about traps, so it's high time for that. As we have only a couple of minutes left, I will pick only a few examples related to when all and when any methods, which often come of use in web applications. For example, if we need to execute multiple HTTP requests as a way of handling single incoming event. Those methods work, of course, perfectly fine, especially when it comes to Sunday scenarios. However, when we start to think about robust way of exception handling, the situation gets a little bit more interesting. So let's take a look at the example. In this sample, I'm just creating a list of 2 tasks. One of them is a good one, the second one is a flaky one. And here we have implementation. Actually, both of those tasks waits for a moment and prints out to the console the fact that they got executed. In addition, a flaky task at the end throws an exception. What we expect here, if we invoke those tasks, this task list using when all method, is that probably both of them would be executed, and in addition, the exception thrown by flaky one shall be handled somewhere there in that catch clause. So let's double check if that's exactly what's going to happen. If we run that code, yeah, both of tasks got executed, and the exception thrown by flaky one was handled. However, of course, it may happen that more than one task throws in such a case. So let's see what's going to happen if I add one more task and run the code again. So as we can see, all of tasks got executed, but only exception thrown by flaky one task was caught here. That might be a little bit surprising when we realize that this flaky 2 task was actually the one that was the quicker, so that if only 100 milliseconds of duration here. That actually reveals 2 pretty dangerous features of when all method. First of all, it just throws only single exception. No matter how many of them are thrown by the list, only single one would be rethrown. And the second is that it's not actually the first task in a chronological precedence that is rethrown, but the order that is defined by that list that is passed here. So the flaky one task is higher on that list, so this is why it was selected. Fortunately, those exceptions are not lost forever. However, they are a little bit more difficult to access. They are stored actually somewhere inside this return value of when all method, and we can access them inside catch clause. But to do that, I need to move this declaration to the outer scope and declare it explicitly. And right now, I have access to our many task object, which inside has property exception of type aggregated exception, which we can access, and that aggregated exception has a convenient method called handle that allows us to define the way of handling every exceptions. And I can just add the same way of handling as for our main exception. In addition, I need to return true value to indicate that I handle that. Otherwise, it will be rethrown. So if I run that code again, you can see that right now, both our exceptions were handled. The situation is still not ideal because flaky one exception was handled 2 times, but it can be easily fixed by adding some other conditions, which is pretty straightforward, so I will not spend time for that. Instead, I will just change that invocation to when any to see what's going to happen right now. So if I run that code right now, we are seeing that at first glance everything is okay. I mean, lucky 2 tasks got executed. That was the quickest one, and this is what when any method was supposed to do. The concerning thing is that no, lucky 2 task was supposed to throw exception. We have our exception catch clause here, and nothing about that in our output. So what happened? So I think that that's pretty, funny signature of when any method, that it actually returns the value that once awaited really waits for the quickest task, but it returns the reference to the task itself. I mean, if you want to have correct behavior in that case, I need to await it 2 times. I need to change the declaration here. And only in that way, if I run the code, I get what I expected. So executed and exception was thrown and handled. I encourage you to read about this when any signature to get more details, as it may be not really straightforward from that place. That's actually all I wanted to show about these potential traps related to HTTP clients, not strictly related to HTTP client, but it came to my mind as it's something that may really happen. It's not a talk about good practices or exception handling. So the only thing I can say about that is I recommend to be really careful when combining exception-driven logic together with when all and when any methods. And ideally, rather to try to handle them inside the task, not trying to do it outside. Anyway, it's high time now to move to the summary section of that talk. There are few items I would like to highlight to recall from our journey from the basics of async awaits to the actual examples in HTTP client. So first of all is that async awaits turns out to be a syntax sugar for callback interfaces, providing a really convenient way of combining them, but are not introducing the asynchrony into the code. And this responsibility is delegated to the awaiters implementation, which are supposed to be able to trigger the callback in a decent way, ideally without blocking a thread. And in case of I/O operations, taking as an example HTTP client, what is used here is a kind of smart multiplexer logic that allows to limit the number of threads that are being blocked rather than not blocking at all. And this is how this real asynchrony is achieved in this case. So that's all I wanted to present today. And then now there will be a short Q&A session. So if you have any questions, you can write them in the chat. And that's all from my side. Thank you. Giving the voice back to Kuba. Thanks.